Hello, and welcome back to DR for Dummies. This is episode 1, the true start of the series. As a reminder, this series is aimed at new DR users who are interested in trying it out in competition for the first time. In this episode, we're going to talk about a short overview of DR and its steps, NISS and scramble switching, how to do NISS tracing, EO or edge orientation, and then a very brief discussion on rNISS. This part is actually optional, which is why I've actually put it at the end of the video out of sync with the other NISS stuff. And all of these are timestamped in the description if you want to skip ahead or come back to anything. Remember, you might have to rewatch certain segments multiple times. This is perfectly okay. There are actually a lot of good resources for these topics already, so feel free to check those out also. I'll mention them throughout the video and put them in the description. Remember, at the end of the day, it doesn't really matter exactly what your internal model is, as long as it works for you. I may explain something better or worse than someone else, so I would recommend taking a quick peek to see if a different explanation makes more or less sense. Anyway, with that out of the way, let's get right into it. I realized I should have mentioned this at the beginning of episode 0, but I never actually gave a high-level overview of what the goals of DR are and how they differ from block building. The core philosophy of DR is to reduce the number of states down gradually until there is just a handful of states that we can solve directly. Specifically, this is done by reducing the types of moves that are required to solve the puzzle. At each stage, the cube gets simpler, and this makes it easier to find optimal solutions. It may be helpful to consider a reduction method on an n by n cube. If you think about it, to solve a 4x4, you do all the operations that require a slice move up front until you get a 3x3. Once that's done, we actually don't need to do any more slice moves, assuming that you don't have parity. So we've kind of restricted the number of moves that are needed. DR works in a similar way. With each step, we restrict the types of moves that are needed until we end up in states that are relatively easy to solve intuitively. In particular, there are at least 3 steps. EO, or edge orientation, in which we remove quarter turns on one axis. DR, or domino reduction, where we remove quarter turns on 2 axes and turn the cube into a domino cube. HTR, or half turn reduction, where we remove quarter turns on all axes. And then sometimes we use floppy reduction also, which removes all moves on one axis. And this turns the cube into a floppy cube or a 3x3x1. We're going to go into detail in each of these steps as the series continues, so don't worry about not getting this right now. You may think that this is somewhat similar to block building, but at least the way that I see it, DR gets its power by being more efficient at removing moves. By the time you get to DR, there are only 10 possible moves that you can make, which means that the branching factor has been significantly reduced from the 18 possible moves that you start out with. By comparison, by the time you get to F12-1, which roughly takes the same number of moves, you still have a large number of moves that you can make, and actually you can't eliminate any of them a priori. This makes DR much more consistent, although FMC is still inherently a very luck-based event. While this isn't like a very rigorous explanation, I wanted to at least mention it to give you an idea of how the methods might differ and what the advantages might be. All right, now talking about NISS. NISS is actually a very well-known tool for FMC and is actually extremely well documented across the internet. As such, I'm not going to give a particularly comprehensive overview here, but I'm actually going to cover more of how to use NISS in practice. If you want a text resource, I'd recommend taking a look at the so-called FMC Bible. For video resources, I highly recommend Kit's video on NISS. It's a bit old and kind of abstract, but for me, it really locked in why NISS works, and so now I can just derive it on the spot rather than thinking about it more like memorizing. If you want something a little bit more practical, Jprim's video is quite direct, and you can also use SCR segment from his mega video on FMC. NISS stands for normal inverse scramble switch, and the fundamental idea is that the normal and the inverse scrambles are linked to each other. So making progress on one side also makes progress on the other. Note that this isn't a DR specific technique. It's actually extremely useful for block building also. To be more specific, you use NISS by starting to work on one side of the scramble, then invert all the moves on that side and apply either the normal scramble or the inverse scramble. This is a process that's called switching, or sometimes called NISSing. If you have an astute eye, you'll notice that your progress is saved after you switch, but the unsolved pieces are in a different place. This is actually not a coincidence and exactly the whole point of NISS. Sometimes it ends up being that the unsolved pieces are easier to solve on one side of the scramble as opposed to the other, and that's what makes NISS really useful. Enough of this theory, let's just jump into an example to get a concrete idea of what's going on. Let's use this scramble as an example. Note that this is a real FMC scramble, not some weird contrived example. I'm going to do block building on this, but it'll still illustrate all the points of NISS. I'm also not really going to explain all the moves I do, just focus on when I NISS and what exactly I do to NISS. With that said, let's try the scramble out. All right, so the first thing I tried was F prime, U prime, F prime, since this made this 2 by 2 by 1, which is pretty nice. The issue is inserting this BR edge is a little bit annoying. The best thing I can think of is 1, 2, 3 moves, and then 4 to solve the 2 by 2 by 2. So let's see if we can NISS and get something nicer on the other side. To NISS, I'm going to take a solved cube and apply the inverse of the moves that I did on the normal. Let's call that sequence 1. To invert, I'm going to reverse the order of the moves and then switch all prime to normal moves and all normal moves to prime. So the inverse of 1 is going to become F, U, F. So if we try that out, F, U, F. Now I'm going to invert the scramble, which is basically just the inverse of the given scramble. So let's try applying that. So now I've applied the inverse. And now that that's done, I've successfully found the inverse state. And interestingly enough, I actually only need one move to make a 2 by 2 by 2, which is significantly more efficient if I were just stuck using the normal. All right, so to notate what I've done so far, I'm actually going to use parentheses to indicate the moves that I've done on inverse. This is pretty common notation and is also used by FMC sites such as Mallard and 333.fm. Of course, when you actually write down your solution, you're not going to need the parentheses, and actually you can't use the parentheses. But for now, let's just write it as this, and I'll show you how to write down your entire solution shortly. Anyway, back to the example. Now let's just continue on inverse a little bit, and we notice that if we do something like DL2, B2, we also get this block here, but it isn't entirely clear how we should use it. So let's try to NISS. So very first thing we're going to do is write that sequence down, and let's just write it down as sequence 3, DL2B2, all right? Now, in order to NISS, we're going to take another solved cube, and we're going to first invert this sequence, sequence 3, then we're going to invert sequence 2. Then we'll do the normal scramble, and then we'll do the moves that we've done. So let's give that a try. All right, so after doing all that, we now notice that if we do just B2, we get this really nice 2 by 2 by 3. And now writing that down, we also notice that we've gotten to this by only doing 8 moves, which is not bad at all. Importantly, I want you to notice how I applied the inverse of 3, then I applied the inverse of 2 in order to switch. That order is actually really important. When you switch to the other side of the scramble, you need to make sure to reverse the orders of the sequences also. Otherwise, you're just going to end up with a bunch of junk. So I'm going to skip ahead a little bit now to the insertion stage. To get there, I found sequence 5 on the inverse, and then sequence 6 on normal. Notice how the inverse I've written inside these parentheses, and the normal I've written without parentheses. Now, in order to do all the insertions, I need to first get everything onto the same side of the scramble, or, in this case, that's going to be the normal. What I'm going to do is I'm going to write down all the moves on the normal first, then I'm going to go through the solution in reverse, inverting all sequences, and then where there's going to be canceling between normal and inverse, I'm going to do that. So let's give that a try. So let's start. We go with sequence 1 first, F prime, U prime, F. Now we jump all the way to sequence 4. This is because this is the next part of the solve that is on the normal. Then we go ahead here, D2, L prime, F prime, D prime, F, D, L. And now we've reached the end of the solution. So we're going to go backwards now, and we're going to take all the things that were on the inverse, and then we're going to invert them. So next we're going to go to sequence 5, and let's invert this. L prime, D2, L prime, D prime, L. Notice that I've also inverted the order here. This D2 is here, not here. Now we continue. We skip 4 because this is on the normal. Next we go to B2, L2, D prime, and then finally U prime. And this is now our skeleton. All of this is now on the normal. So if we apply the scramble, then apply this sequence of moves, we're going to end up with 5C, just as we did when we were doing all of our switching stuff. One thing I want you to notice is this is where we switched from normal to inverse. And if you notice, L and L prime actually cancel each other out. So we've actually saved 2 moves there while doing the switch. The other thing is D and D2 also cancel. D2 I can go away, and we can actually just turn this into D prime. So even though originally this was 20 moves, this is now 17 moves to 5C. Canceling 3 moves while switching is actually pretty rare, but it is certainly possible to cancel 1 and sometimes 2. Now that I have all of this, I can actually just do an insertion now. So I've gone ahead and rewrote the skeleton by canceling those moves. And it turns out that there are 2 places where you can put insertions, 8 minus 5 and 8 minus 2. That means that after this 17 moves, you can insert 9 moves into here, and you end up with a 26 move solution, which is pretty good for block building. And with that, you should have a full example of how to use NISS during a solve. I want to address one question that you might have. Writing down or utilizing the moves of the inverse is explicitly disallowed in FMC. So how is it legal to use NISS? Well, the short answer is you should just trust me that it's allowed. I'm a delegate after all. But the longer but still somewhat short answer is that we're not actually using the moves of the inverse, and rather we're just kind of using it as a singular black box to give us either the scramble state or the inverse scramble state. Any more explanation really gets into some mathematical territory, which is not really the goal of this video. Maybe I'll make a different video on it, or maybe I'll put it as an appendix to this series. But the takeaway is you can use NISS, just don't use the specific moves from the scramble itself. All right, I now want to cover the topic of NISS tracing, and a good place to start is the concept of pseudoblocks. In this example that we did before, there were 2 cases where we had a block that was made, and it was relative to the other pieces. You can see that like this kind of looks like a block, but it looks like it's like 1 move off, and same thing here. In cases like this, if you NISS, you will actually always be able to solve the block in 1 move. This is not a coincidence actually, and this is the technique of pseudoblocks. And actually, this technique doesn't just apply to blocks, but actually applies to every single piece on the cube. If you master this, in your mind's eye, you can quickly check where the pieces are going to be on the inverse without having to do the switching physically. The only thing you need to remember is how pieces on the normal correlate to pieces on the inverse. We already know that solved pieces on one side will be already solved on the other, but we can generalize this statement by making this observation. If sticker A is in position B on the normal, then sticker B in position A will be on the inverse. But what does this actually mean? Let's take a look at some basic examples. For the first example, let's take a look at a very, very simple scramble, the one that I have here. Let's take a look at the piece that's sitting in UFR. This is the FLD sticker, which belongs here. UFR, FLD. So this means that FLD is sitting in UFR. Let's make a note of that. Now let's take a look at the inverse, which is this one here. If we apply this rule, we should expect to see UFR sitting in FLD. Let's take a look at the FLD sticker. Okay, well that's here. And the piece that's sitting here is indeed UFR because it belongs over here. So we found that on the normal, FLD in UFR, and on the inverse, UFR in FLD, which then shows that this indeed holds. The same is actually true for the other pieces that are misplaced. You can take a quick look. For example, here on the normal scramble, here's that UFR sticker, and it's currently sitting in RFD. So now if we look at UFR now, we find that the sticker that's sitting there is indeed the RFD sticker. And that'll hold for the other ones that are misplaced. One thing that's interesting is it actually holds for solved pieces also. Back to the normal, if we look at the UF sticker, that sticker is sitting right here. So we see that UF is sitting in UF. So now in the inverse, if we switch those, we also expect UF to be sitting in UF, and certainly that's the case. But UF and UF, that simply means that the piece is solved, which means that now we know that the piece is guaranteed to be solved on both sides. So now we've shown that the rule applies actually for all pieces on the cube, not just misplaced ones. Let's take a look at the previous scramble that I used to demonstrate NISS. So here on the normal, let's take a look at the FL sticker. That sticker is currently sitting in BL. So the FL sticker, the one that's supposed to be here, is sitting in BL, back here. So maybe let's write that down. Now in the inverse, which is over here, if we look at the FL spot, we see that BL is sitting here, which is exactly what we expected. If you want to do an exercise, you can actually do this yourself. The normal and the inverse are here, and you can check that this actually holds for all pieces. Now that we have this nifty little tool, let's see what kind of information we can get after just doing a couple moves. If we do FU prime F prime as before, we get this pseudo block. Now let's trace some of the pieces of the pseudo block and see where they're going to end up on the inverse. We see that UB is sitting in UR, and UR is sitting in UF, and UBR is sitting in UFR. You can confirm that all of this is the case just by yourself or at home. So now let's try and guess where this is going to be on the inverse. UB and UR means that UR is going to be in UB. UF and UR means that UF is going to be in UR, and UFR is going to end up in UBR on the inverse. So let's see if that's actually the case. I've done the inverse here by inverting these moves and then inverting these moves. And now let's take a look at this. In the UB spot, we find that the UR piece is there, so this is correct. In the UR spot, we find that the UF piece is there, so that's also right. And in UBR, we find that UFR is there as well. So one thing that's interesting is we see that the entire 2x2x1 block ends up back here. The final thing I want you to note is that FR is already solved, and it's solved on both sides. So we see that we have this big block here, and FR is here as well. So that means that we only need to do one single U move, and we end up with the whole 2x2x2 solved. So there are two key takeaways from this exercise. One is that the normal and the inverse scrambles are innately linked, but instead of just the pieces being random, the locations on one side tell you exactly where they're going to be on the other, just by using this little trick. The second thing is that blocks actually get preserved across NISS, as we just demonstrated. You can do a little bit more rigorous proof to show exactly why that's the case, but I hope that the little demonstration was good enough to convince you. So all you need to do is remember this. Sticker A, position B on normal, means sticker B in position A on inverse. Be careful that it's the sticker, not just the piece. Bringing the topic back to DR, while it isn't strictly required to know how to do NISS tracing, it can make checking solutions significantly faster. In the video on how to get to HDR, I'm going to make extensive use of NISS tracing in order to simplify all the corner cases. Instead of having to memorize all of them or having the whole hyperparity maze, we can reduce the complexity significantly by using NISS tracing. But we can refresh on that once we get there in a couple weeks. That wraps up the discussion on NISS. I hope I've convinced you that it's a useful tool to have in your toolbox. However, you may notice that I haven't actually told you when the best time to use it is, and I'm not going to in this video. We have a lot to get to, and we're only like halfway through, but let me know if this is something you're interested in, and I'll make a note in the advanced topics video at the end of the series. In the meantime, enjoy using this hammer I've given you on many, many nails in FMC. All right, now that we've gotten NISS out of the way, let's switch gears and discuss edge orientation, the first step of DR. Edge orientation is more commonly called EO, and if you've ever heard of ZZ, or even if you know about OLL, you have some idea of how EO works. Because of that, EO is actually extremely well covered in a lot of other tutorials, so you're actually spoiled for choice in terms of other resources. You can use the FMC Bible, the DR document, JPerm, and SER all have EO guides that you can use as reference. A little bit of a fair warning, the way that I teach EO is a little bit different and actually a little bit closer to how EO is used in speed solving, so you might notice some discrepancies if you use this video compared to other resources. Before we can solve EO, we have to first learn what it means for a cube to have EO solved. Simply put, there's this definition. A cube has EO solved relative to an axis if all pieces can be solved without using quarter turns on the front or back faces. This is a little bit of a mouthful, so let's break down some pieces of the definition. So what does it mean to be relative to an axis? This means that EO is orientation dependent. That means that in general, when you do a rotation, you might not have EO anymore. Right now, I have EO relative to this green front, but if I rotate and do Y or Y prime, I no longer have EO anymore. X rotations and Y rotations will break EO, but Z rotations always preserve EO no matter what state it's in, if it's solved or unsolved. No quarter turns on F or B. This just means that the moves F, B, F prime, and B prime are not allowed. If you try and get away with this by doing rotations, well, you already know that EO is not necessarily guaranteed to be the same. So you can't get out of it by doing rotations either. Importantly, F2 and B2 are still allowed because they're not, instead of being a quarter turn, they're more like a half turn. So I'm going to refer to these quarter turns relatively often as far as DR is concerned. So we're going to see these in several places. So here's an example of a cube that's not in EO. You'll see that a couple of these edges cannot be solved using only RL, U, and D moves. For example, this edge is going to end up flipped in place. The only way to have it unflipped is to do a quarter turn on F in order to keep it that way. Same thing goes for this one, and this edge. All of these are unoriented edges. By contrast, every other edge is already oriented. This one is obviously oriented because it's in the solved position and it's just fine. This one is not in the solved position, but I don't have to do an F or B move in order to make it solved. So that one is also good. And you can go through and check the rest of these, but I'll show you how to do that later. Because EO is relative to the axis you choose, there are 3 different axes that you can use to check EO on each side of the scramble. The ones that I use are green front, orange front, and yellow front. Although you can equivalently do any sort of Y2, and you get this, they're all equivalent. Using the previous definition of EO can be a little cumbersome in an actual solve, so here's an equivalent process that I use. EO is relative to the axis, as we discussed before, so you need to pick one of the several front colors. There are only 3 front colors to choose from. You can either choose green front, orange front, or yellow front. At least those are the ones that I choose. If you do a Y2 rotation, then you end up with the same case. The next thing you're going to do is apply this decision tree for all of the following pieces. All of the stickers that are on the L and R, FU, FD, BU, and BD. So we're going to try and apply this decision tree to all of those stickers. Let's give it a try. The first thing that we're going to do is we're going to check if the sticker is an L or R color. So in this case, L and R are orange and red. So if it is, then the edge is always good. For example, this edge. I don't even need to check this sticker because seeing this, it's an R color, and therefore this edge is always good. I can always orient this edge without doing any F or B quarter turns. If it isn't an L or R color, next we ask if it's a U or D color. If it is, the edge is always bad. Here's an example of that one. So this sticker is on the R side, and this is the D color. Because this color is D, there's no way that I can put this edge into its spot without it being twisted. In other words, I have to do an F or F prime move in order to solve this edge, and therefore this edge is bad. The final case is if you can get an F or B color. In this one, you actually can't immediately tell if it's good or bad, and you have to do another decision tree. You have to check if the adjacent color to that edge that is U or D. If it is, then that edge is actually good. This is actually incorrect here. Yeah, so if the other color is U or D, then it's actually good. And if it's not U or D, then that edge is guaranteed bad. This edge is blue, which is an F or B color. So what I need to do is I need to check its adjacent sticker, which is this one. This sticker is not a U or D sticker, which means that I cannot orient this edge without doing F or B. In other words, it's not oriented. And you can see this. If I try and place this edge where it's supposed to go, it ends up being twisted. And that means that the edge is not oriented and that it needs an F or B move. On the flip side, let's take a look at this edge. This edge is also an F or B color, so we can't immediately know if it's good or bad. But if we check this sticker, we see that this sticker is a U or D color. And based on our decision tree, that should give that it's yes, it's good. And we can see that. I can put this edge back here, and then I can do B2. Remember that B2 is allowed, and it doesn't change EO. And now this edge is solved. Therefore, this edge was always good to begin with. And remember, we want to apply it to these 4 edge stickers, these 4 edge stickers, these 2 in the front, and these 2. By applying it to these stickers in particular, you cover all of the edges, and that way you can check if all 12 edges are good or bad while looking at approximately 12 to 16 stickers. Notice that this is actually different than basically every other resource that you'll see on the internet. The other resources, instead of checking L and R, check U and D, and then they check different stickers on F and B. So if you do it that way, that's perfectly fine. You get basically the exact same thing. You'll get a different decision tree, but you'll end up with the same conclusion as to which edges are good or bad. This is just the one that I prefer and comes from speed solving. So now using this method, we can now count the number of bad edges and find where they're located. So this is the same scramble as the NISS example from before. And if we use this, we can figure out how many edges there are. So let's give that a try. First, we need to pick an axis. So let's start on green axis for now. We're actually just going to check all axes, but let's just start on green for now. Next, we apply our decision tree. So let's go through that for each of the 12 edges that we see here. Let's start with this one. This edge is an L or R, so this one is always good. This one is U and D. This one is bad. This one is an F and B edge, so we don't know if it's good or bad, so we need to check the adjacent sticker. This sticker is an L or R sticker. This means that this one is also bad. This one is an L or R sticker, so this one is good. So far we have 2 good and 2 bad, and in particular, the 2 bad are right here. Next, I move over to R. This one is F or B, so we check this one, and it turns out that this is UD, so this one is good. This one is L, it's automatically good, and then these 2 are U and D, so these 2 are automatically bad. Next, moving to these, on F, we only check the U and D stickers. Both of these are RL, so those are good. And then the same thing in the back. We see that the 2 UD stickers are both RL, so those are also good. This gives us our 4 bad edges. Here, 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 and here. Let's now take a look on the L axis. LR is sometimes what we call it. You can also call it orange front. Let's try and go a little bit faster here. This one is definitely good. This one is definitely bad. These 2 could be good or bad, and we see that this one is good and this one is good. So far, we only have 1 bad. This one is bad. The reason is because this is an FB sticker, and this one is not UD. That means that this one is bad. These 2 are both good, and this one is also good. So we're at 2. This one, remember, is an LR sticker. Previously, this one would have been bad, but because we rotated, we've changed the orientation of the sticker, and now we can solve this without using F or B moves. So this one is good. This one is bad. It has UD on the front. Same thing with this one. That one is also bad, and this one is perfectly fine. So this one has 4, and they are in here, 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 and here. Let's now go to the hardest one, for at least what I find that most people struggle with the most. And honestly, I'm probably the slowest at this one as well. This is yellow front, or equivalently white front. This piece immediately you might be suspicious of because this is an F color. But if we take a look at the back, this one is actually a D color here. Remember, D is blue. So this one is actually good. We don't need to do anything. This one is the only bad one on this side. So let's make a mental note of that one. This one is good, and this one is also good. And these are for the same reason as this one. This one is also good. This one is guaranteed bad because this is a U color. So let's mark that one. These 2 are a little bit tricky, but both of these are bad actually. The reason being that this is actually an F color, this is a B color, and this one is an F color, and these 2 are not UD colors, so both of those are bad. And now we switch to the back here. This one is definitely bad because it's a D color. This one is also bad because it's a B color, and then the other color is not a UD color. So total, we've ended up with 6 on this side. So 4 on this axis, 4 on this axis, and 6 bad on this axis. We're almost ready to learn how to solve EO, but there's a couple of important properties we need to know. Firstly, moves other than F or B don't change EO at all. Conversely, F and B quarter turns flip the EO of all four edges on that face, from good to bad and bad to good. Secondly, the number of bad edges is preserved across NISS, but their locations are not necessarily preserved. Number 3, you may have noticed that in the example, the bad edges always came in evens. This is actually always the case. If you get an odd count, you either miscounted or your cube is not in a valid state. The reason why odd EO is not allowed is the same reason why you can't flip an edge normally. And as I mentioned before, Z and Z prime are the only quarter turns that don't affect EO. This is going to be useful when we try and find DRs in the next video. The other thing is half rotations like Y2 and X2, these don't affect EO either. This is why there are only 3 axes that you need to consider on each side of the scramble. If you do Y2, then you just turn orange into red, and that doesn't affect EO at all, so there's just no point in checking it. They're exactly the same. Using the first of those 4 properties is actually the most useful, since it tells us how we can solve EO. We basically need to get all 4 bad edges onto the same F or B face, and then if we do a quarter turn, we just turn all of them into good edges. Solving 4 is actually pretty easy then. Just note that you can't use any F or B quarter turn to get them onto the same face. 8 bad edges is pretty similar. All you need to do is get 4 onto one face, do a quarter turn to make those good, and then you'll have 4 other ones, get those onto the same face, make those good. 12 is also similar, although you don't really want to see 12 in any given scramble. 10 bad is also a pretty bad case, but you can get 4 of them onto one face and then do a quarter turn and you can reduce to 6 bad. If you do 6, now the things get a little bit tricky. You could take 4 of those 6 bad edges and then make them good, but then you're left with 2 bad edges, and what do we do now? We only know how to switch 4 bad at any given time. Let's take a look at this contrived example where there are only 2 bad edges. We know that these 2 edges are bad because they're the only ones that are flipped in place. Everything else is solved. Now, the way that we can solve this actually is to put one of the bad edges on either F or B, like is already done here, and then we do a quarter turn. By doing this, that bad edge is now good. We can check because this color on the R side is one of the F or B colors, but then this color is a U or D color. So this one is good. So that one became good, which is great. But now we have 3 other edges which have become bad. Remember, these were all solved before and we did an F, so now in order to solve them, we'd have to do another F turn. Well, if we do some quick math, we started with 2 bad edges, we got rid of one of them, and then we added 3 more. Well, now we have a grand total of 4 bad edges, which is pretty convenient, because now we can just do this like normal. If we check where our bad edges are, they're here, 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 and here. So if we just get them all onto the same face and do a quarter turn, well, now we actually have all of our edges solved. In other words, in order to solve 2 bad, what we have to do is take one of them, solve that one, but then break EO on the other 3, and we just reduce it to a 4 bad case, which fills in our question mark here, which also ends up being reduced to 4. You'll notice that there's still a question mark here next to 6. And actually, there is one trick I want to point out. Sometimes the only option is to solve 4 bad edges and then you solve the remaining 2 as I previously mentioned. But actually, oftentimes it's optimal to solve 3 edges first, and that leaves 4 bad edges. Let's take a look at this one, for example. On the FB axis, we have 3 bad edges on F and 3 bad edges on B. The bad edges are here, here, here on F, and on B, the bad edges are here, here, and here. One thing you could do is you could put one of the bad edges into the back here, do a quarter turn, and now you're left with these 2. So in order to do that, we did one move to do this, and then one more move to orient those 4. And now to orient these, we're going to need 4 more moves. So that would take 6 moves total. The question is, can we do any better? Well, it turns out that the answer is yes. If we do a quarter turn while we have 3 bad edges on F, we're actually left with 4 bad edges total. The bad edges on B didn't change. They're still here, here, and here. But now this is the edge that's bad on F. And if you notice, now that we have 4 bad edges, we can actually put them all onto the same face and do a quarter turn to solve EO for all of the edges. The other way, we had to solve 4 edges first. That required 2 moves. Then in order to solve the other 4, it required 4 more moves, which was 6 moves total, whereas this one only took 3. Similar to the other flowchart, it might be helpful to think of EO in the same way. 12 goes to 8, goes to 4, goes to 0, and then 10 goes to 6, which could either go to 2 or 4, and 2 always goes to 4, which goes to 0. I think I read somewhere that EO can always be done in 7 moves, but most FMCers will only consider EOs that are in 5 moves. Unless you get a horrendous scramble, in which case maybe you extend it, but 5 or less is typically the goal. Now onto some tips and pointers for EO, particularly when you're using DR. You want to find as many EOs as possible. This is actually pretty different compared to using EO for ZZ or other speed solving methods. The reason why you want to is because each EO has the potential to give you a different case, some of which might be easier and some of which might be harder getting to DR. We're going to go over those, the ones that are going to be better and worse next week. If you have to do 2 quarter turns and one of them is the middle of EO, you can do that quarter turn in either direction and maintain EO still. Here's an example. Note that the edges that are bad are here, 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 and here. We already have 4 on this side, so we have 2 choices. We can either do F or we can do F prime. Both of them will orient the edges that are here. So let's say that you decide to do F, then U prime B. You'll find that this is in EO. However, clearly doing F prime, U prime, B prime was the better choice. Even though there were 2 different options, they gave us 2 completely different DRs in some sense. That's why you want to check if swapping one of the quarter turns will give you a better case. On this note, you actually can't invert the quarter turn at the end of EO. Well, I guess in theory you could, but it doesn't give you a fundamentally different EO solution, and it doesn't give you any better of a case going into DR. Maybe you should just take that for granted for now, and I'll show you why in the next video. We move to point number 3 now, in which double moves are actually allowed. Remember this, just because you can't do F and B doesn't mean that you can't do F2 and B2. Here's an example. The bad edge is here, 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 and here in the back bottom. Without using F or B moves, it would take you 5 moves to solve this EO. But if you do, if you do allow double moves, you can do F2, D2, F, and now you'll notice that EO is solved. Now, as an addendum, you should definitely write down 5 movers as well. Just because it isn't the most efficient doesn't mean it's not worth considering. In this example, actually, even though that there's a 3-move EO, the 5-move EO actually is going to solve the entire cube. And so therefore, that's the one you would have wanted to pick. But if you only wrote down the 3-move EO, you would never have found something like that. So check the EOs up to 5 moves. Moving on to this point now, sometimes you'll want to insert moves that don't do anything or don't affect EO. The reason why is you can still get valid EOs by doing it, and sometimes doing the extra moves can give you better cases. Here's one particular example. The bad edges are here, 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 and here. So using our double moves from before, one thing you can do is do F2, U prime, F, and this will certainly solve EO. But you may have noticed that we can actually do D, D2, or D prime, and all of them don't affect EO. In other words, we always get a valid EO. This is because all the pieces that are on this D layer already have EO done. And so changing them doesn't do anything to EO. And in fact, it turns out that if you do D2, you actually get the optimal solution. This next point has to do with checking both sides of the scramble, both normal and inverse. Just because there's no short EOs on normal doesn't mean that the inverse is also guaranteed to be bad. And even if both sides are bad, you can get different cases into DR. One of them might be good and one of them might be bad. So definitely make sure to check both sides. And finally, to briefly cover it, there is a technique called NISS EO, and I'm going to cover that in detail in the advanced topics at the end of the series. But very briefly, the idea involves using NISS switching in the middle of EO. Normally that's a little bit tricky, but you can use NISS tracing to figure out if 4 edges are on the same face on the inverse. If that is the case, you can write that move down immediately and then eliminate those 4 edges from the normal side, and then you continue with the rest of the EO. The reason for doing this is essentially switching after just one move on the inverse but you don't actually have to do the inverse scramble itself. It's mostly useful on scrambles with 6 and 8 bad edges, and it can help you get simpler cases to work with. If this didn't make any sense at all, it's absolutely fine. We'll see more in episode 5. And the last thing I wanted to mention is that the Hitchhiker's DR Guide actually has a ton of useful information, even beyond the stuff that I'm sharing here. So I'd recommend taking a look at that if you want to see more info. And actually, just one more thing to mention. EO can also be useful for block builders as well. In particular, it's a lot easier to find insertions with edges that are either solved or oriented at the end of the skeleton. At least I found it significantly harder to do pure edge comms with unoriented edges, although by the time that I got to that point with block building, I had already started switching to DR anyway. I do find it a lot easier to solve pieces that are oriented, and once you get to a 2x2x3 with edges oriented, then your cube is actually just reduced to 2gen, which significantly reduces the complexity. So even if you're just going to do block building, I would recommend at least learning some EO techniques. All right, and very, very briefly at the end of the video, I wanted to discuss rNISS. rNISS might be the worst named technique in FMC. Supposedly it stands for reverse NISS, but it doesn't really make that much sense to me. Honestly, I would have personally gone for something like sequence splitting, but I think the term is completely entrenched now, so there's nothing that we can do about it. The main idea of rNISS is you want to be able to NISS anywhere, not just at the step boundaries. In the previous NISS example, we switched at the end of relatively defined sequences, and rNISS extends this idea by picking any point in the solution or skeleton to NISS from. It is particularly useful when it comes to insertions, particularly edge insertions and slice insertions, and because of that, we're going to see more of that in episode 4, which is why I'm only briefly mentioning it here. To give a quick example, let's return to the NISS solution skeleton from before. One way to do insertions is by using marked stickers to keep track of which pieces need to go where and in which orientation. The problem is this can be a little bit hectic because you end up seeing a bunch of pieces that are unsolved, and it's a little bit hard to track what's going on. So an alternative method is rNISS. Let's give rNISS a try here. The first thing we need to do is pick a spot from which to rNISS, which I'm going to call the rNISS spot. I'm going to mark that here by this vertical bar. The next thing we're going to do is execute all moves after the rNISS spots exactly the way that they're written. In other words, we're not going to invert it or do anything special. Okay, after those moves, the next thing that we're going to do is now apply the scramble, also exactly as we see. So just do the normal. Okay, beautiful. The final thing that we're going to do is now execute the rest of the skeleton, starting from the beginning and going all the way up until the rNISS point. Again, just do it exactly as normal. And once you do all that, you notice that we started off with a 5C, and even after doing this rNISS nonsense, we've also ended up with exactly 5C once again. That's certainly very interesting, and that means that here you can also do an insertion, and in particular, if you find a good one, you can do a particularly nice insertion. One thing that you can note is if you actually, this spot I didn't just pick it arbitrarily, this spot is actually a spot where you can do 8-5 insertion. That particular one looks like this one here. So just executing these moves, you can see that it solved 2 of those pieces, and now we're left with just 3C. This was a particularly good one because it canceled 1 move on this side and 2 moves here because this L and L prime cancel exactly. So this was a particularly good one to pick. And it was easier to use rNISS to do this rather than using stickers, because in using rNISS, we just had to execute this exactly as we see it, execute the scramble exactly as we see it, and then the remaining part of the skeleton just exactly. At no point did we have to like manually or invert things kind of in our head. Instead, if you were to use stickers, you'd have to execute the scramble, then execute the entire skeleton, and then reverse these moves, and you'd have to do that in your head, or you'd have to waste time like writing this out. And you can imagine if you're checking every single position, rewriting the second part of the skeleton would be quite cumbersome. So this is one way to do it in fewer moves overall, and you're less likely to make mistakes. That's everything I wanted to cover about rNISS. It's covered in a couple other places. I don't think it's covered particularly well, but it is covered in the FMC Bible and also SCR's video. So you can take a look at those if you don't want to wait for my video on edge insertions and slice insertions, which is going to come in a couple weeks. And with that, we're done with episode 1. All the essentials have been wrapped up. You'll need to have this stuff down pretty pat for DR, simply because these techniques are just exceptionally useful. I mean, technically, you don't really need NISS. If you've heard of Jacob Sherwin-Brown, his 16 FMC single, you actually didn't need to NISS on that one. But if you don't use NISS, you're kind of playing with a handicap here. Some of this stuff is probably a review for many of you, but there's still quite a lot of stuff that ended up getting covered. This is going to be a pretty long video, all things considered. If this is your introduction, I'd especially recommend rewatching and reading other sources just so you can figure out what's trying to go on. If you want to ask questions, I'll be pretty responsive in the comments, so let me know if something is confusing, and also just let me know if something is wrong, or if there are other resources that you want to point to. With that all said, we're done here. I'll see you all in episode 2. We're going to discuss RZP and how to get to DR, and finally actually start using some DR stuff. See you later.